Hey guys, this is Mr. Malm again. Don't forget you have to have watched the part one. This is part two, and this won't make sense until you see part one. So if this is your first time and you haven't seen part one, you got to see part one, you guys. So the goodness of fit test, chi-squared test. Okay, see part one. All right, let's go ahead and begin. Let's finish that problem here. So step two, choose the appropriate inference procedure. Okay, we're going to use a chi-squared goodness of fit test because there's more than one, you guys. If there's only two, we do a z-score test, you guys. But there's more than one, so we're going to do the chi-squared goodness of fit test to measure the strength of the evidence against the hypothesized distribution, provided that the expected cell counts are large enough. So here's the expected counts right here, you guys. Okay, so remember, there's 200, you guys, and so it was I multiplied by the percentages that we got from that chart with the 16 on there. So 9/16 gave me 0.5625. So I multiplied 200 times 0.5625, and then 200 times these other percentages, and these are my expected counts. These are my E's. All right, so since all the expected counts are greater than 5, we can proceed with this test. That was one of the requirements. So carry out the inference procedure. Okay, so it's O minus E squared divided by E, and it's the sum of all of these. That's what chi-squared is the sum of all of these. Okay, so this was the observed count. The first one was 101 minus the expected count, 112.5, divided by the 112.5. Okay, and we added them all up, and I think and so, oh, this is the wording right here. So this is where we got of the 200 offspring. So that I just went back to where we got these numbers from, okay? And then so that added up to 5.742, okay? And so since there were four different types, you guys, then the degrees of freedom is 3. So table E shows in our test falls between, okay, so this, pull your book open again, okay, go down on, see, I got my book open. Do you hear it? Here we go. Okay, get your book open. All right, so table E, and then go across and look for the 5.742. Okay, and I see 5.32 on degrees of freedom of 2, and then 6.25. All right, so if you look right up on top of that, you guys, it's falling between, look up on top, it's falling between the 15 and 10% significance level. All right, and the calculator, I'll show you in just a minute how to do it in the calculator. Uh, it gives me about 12.5% right there, so it falls a little bit short right there. So step 4, interpret your results. Okay, the p-value is 0.1248, indicates that the probability of obtaining a sample of 200 fruit flies offspring in which the proportions differ from the hypothesized value by at least as much as the ones in our sample is over 12%, assuming that the null hypothesis is true. So that is not sufficient evidence to reject the biologist's prediction that it would be different in one of those categories. Okay, so are you married? Here we go. So this is going to be this table right here. All right, we're going to use these tables right here. So according to 2000 current population survey, the marital status distribution of the United States adults is as follows. So married, never been married gives me these percentages. I think we worked on this a while ago, you guys. Okay, so here's a random sample of 500 U.S. males aged 25 to 29 years old. All right, and yield the following frequency distributions. Okay, so of the 500, so of the 25 right here, I'm going to come back to these numbers. 260 were never married. 260 out of the 500. Okay, that's like 50-something%, you guys. All right, so the population parameters are: we wish to see if our SRS differs from. Oops, that should be THE right there. Differs from the. You guys get the idea. HE from the survey. Let me save that. I'll save that at the end. All right. So my null hypothesis is the marital status of the males 25 to 29 equals the population as a whole. Okay, and your null or alternative is that they don't equal the population. So the conditions are: we can use the chi-squared goodness of fit test to measure the strength of the evidence against the hypothesis test, providing that the expected counts are large enough, which means they're greater than or equal to 5. So here's my expected counts, you guys. Okay, so I took the percentages that we got in that first table, the one up on top, times 500. Okay, 500 times each one. And all of these numbers, the 140, the 281, the 32, and the 46, are all greater than 5, so we can proceed. Okay. All right, so let's carry out the inference procedure. Okay, this is how we do it in our graphing calculator. put in list 1 the 260, 220, 0, and the 20. And I got those from right here, you guys. These are my observed. Okay, so these, remember, I go observed minus expected. All right, and then the expected, we just did that, you guys. So those go in list 2. We just did that back right there. These are the expected counts right there. So we didn't do that for nothing, you guys. Okay, so that goes in list 2. All right, and then go back to a blank screen. So list 1 minus list 2 squared divided by list 2, and this little arrow means store, and there's an STO button in the bottom left. So we're going to store all of that in list 3. All right, so that's going to give me, and then to sum them all up, because we have to add them all up. So you go to list, and then second function stats, you guys, which is, I'm sorry, list, which is above the stats, you guys, which is second function stats. You scroll over to the math, and then number 5 for the sum. Okay, so then put in the sum of list 3, and you should get 161.77. If you haven't picked up a calculator yet, pause it right here and get busy. All right, and then calculate your chi-squared. So your chi-squared CDF is in the distribution. It's in distribution, which is in above the vars button. And my calculator was number 7. So you do chi-squared, and then you do answer, and your answer is above that negative key in the bottom right-hand corner. So you do chi-squared, and then do shift answer to get that. And then 1,000, and you do 1,000, you guys, is because your chi-squared goes way out, so we just want a big number, so it gives us the whole curve underneath the curve. I could pick 1,000,000 if you wanted to, but I just did 1,000. I think 100's even enough, or 500. And then do 3 for degrees of freedom. Okay, and then enter, and then it gives me this number right here, 7.6 times 10 to the negative 35. That means that decimal goes to the left 35 spots, so that makes the p-value extremely tiny. Okay, so just explain that 1,000 right there. So interpret your results. All right, there's overwhelming evidence to reject HO, and the distributions must have to be different. There we go.